Deux mots, je suis Philippe Clermont, je suis le président de l'association Planète Mars depuis quelques mois. Et nous sommes en train de relancer une dynamique de conférences, d'occasion de convivialité où on puisse échanger. Alors on a eu un succès assez important parmi les visiteurs qui sont venus, puisque vous êtes à peu près 90. Donc on a une limite de capacité de salle, on a pris une petite charge qui est remplie. Donc nous sommes, merci d'être venus, et j'espère que la conférence va vous intéresser. Deux mots sur l'association Planète Mars. Nous sommes donc, tout le monde n'en est pas membre ici, c'est super, il y a une vingtaine de membres ici. Donc l'association Planète Mars est la branche française de la Mars Society. C'est la branche française mais indépendante, c'est un réseau d'associations qui fonctionne, qui échangent, qui partagent des formations, qui partagent des conférences. Et je voulais signaler d'ailleurs à cette occasion ce week-end prochain en Suisse, près de Neuchâtel, à la Chaux-de-Fonds, se tient la Convention européenne des Mars Society. Donc tout un ensemble de conférences de spécialistes européens de Mars qui vont faire des exposés. Alors que fait l'association Planète Mars et la Mars Society? L'objectif, c'est de promouvoir l'exploration robotique et humaine de Mars. Promouvoir alors d'une manière assez large, en pratique l'activité, qu'est-ce que c'est? C'est faire des conférences, c'est aller faire des conférences dans des écoles, dans des conférences comme ce soir. C'est aussi encadrer des étudiants. Actuellement, par exemple, il y a 6 stages étudiants qui sont encadrés par des membres de l'association. C'est aussi organiser des séjours en simulation, ce qu'on appelle la simulation analogique, c'est-à-dire la capacité dans un lieu fermé, isolé, en respectant des protocoles, comme si on était sur Mars pour faire des sorties. Les scaphandres, c'est la possibilité de bloquer une équipe typiquement de 6 personnes qui vont vivre en autarcie avec un programme scientifique et en s'astreignant à des sorties comme si on était sur Mars. Qui publie des résultats dans lesquels il y a une démarche organisée. Donc il y a 2 stations qui sont gérées par la Mars Society. Il y a donc MDRS qui se trouve dans l'Utah et F-Mars qui se trouve dans le Grand Nord canadien. Donc des conditions qui ressemblent un petit peu à Mars, en termes visuels déjà communs, et en termes de conditions pas forcément très agréables, dans l'environnement un peu difficile autour. Alors j'en ai assez dit, on est plusieurs membres de l'association. L'organisation de la soirée, c'est que Robert va donc nous faire une conférence qui va durer à peu près 1 heure. Après on aura une session de questions-réponses qui peut durer jusqu'à 21 heures. Il y a des boissons, on pourra avoir un événement convivial. Alors maintenant, je vais quand même présenter Robert Zubrin. Je ne sais pas si tout le monde le connaît ou pas. Tous ceux qui sont intéressés à la Mars Society, à Mars, le connaissent certainement, puisque Robert a révolutionné la manière, l'architecture de mission pour aller sur Mars. Il a cassé l'idée qui était initialement de Werner von Braun, puisque Werner von Braun avait des idées d'architecture pour aller sur Mars, avec des véhicules extrêmement complexes. Robert a défini le scénario de Mars Direct, qu'il a publié dans les années Mars Direct was published around 1990. So Robert is a PhD in nuclear physics, nuclear engineering, astronautic engineer. He started working at Martin Marietta, and then you were, in 1998, founder of the Mars Society. And the year after, the French chapter was created by several people, but 2 of them, mostly well known, Richard Heidman and Alain Souchy. And Richard Heidman is vice president at that time. He's not currently present this evening. He's sorry for this. I think I can that you speak, because I'm taking too much time, in fact. Okay?
Bonsoir. Merci pour votre interest. That's it. All right. I'm going to talk about my Mars plan, but before I do that, I'm going to make some observations about the time that we're in, and I'll come back to that at the end as well. About the time the Mars Society was formed in the 90s, there were books being published with titles like The End of History, The End of Science. Everything worth doing has been done. Everything worth knowing is known. Okay. It was interesting for a while. Sorry you missed it. It's over. I think, well, a lot of people, frankly, some people took this seriously, some people were quite skeptical. I was certainly skeptical. But the 20 years since has proven these things couldn't have been more wrong. We certainly weren't living either the end of history or the end of science in the 1990s. I'll leave history to one side for a moment, but certainly science. What we've had since the 90s has been a great age of science, and I'll just refer to my own field, which is space exploration. We have made incredible discoveries with probes to Mars, to the outer solar system, with the Kepler Space Telescope discovering thousands of worlds. I was at a talk a month ago in which Sarah Seeker, leading astronomer, got up and said, based on the Kepler and other observations, we now believe that 1 out of 5 stars has an Earth-like planet in its habitable zone. 1 out of 5. That means in the Milky Way galaxy, there are 80 billion Earths. And there's billions of galaxies. That's incredible, okay? We're discovering hints of new forces of nature. And then with respect to our own solar system, we just talk about the past year, okay? And we're just talking about Mars. We have the European Mars Express, using ground-penetrating radar, has discovered an underground lake on Mars, liquid water. That is a habitable location. And look, if there's one underground lake on Mars, there's hundreds. Okay. You know, if one is there, it means it's possible for them to be there. They'll be all over the place. People have been suspecting for a while that there was a liquid water table underground on Mars. This proves it. Just yesterday, a paper was published showing that these reservoirs are probably oxygenated, which means that they can support not just bacteria, but higher life. By higher life, I don't mean fish and people, but I do mean much more developed types of microorganisms than bacteria. So if there was ever life on the Martian surface, and there's every reason to believe there was once life on the Martian surface, it's probably surviving underground on Mars today. Also this year, the American Mars Reconnaissance Orbiter, also using ground-penetrating radar, this is proving to be a field whose time has come, a form of instrument that has matured, has discovered glaciers on Mars in the northern hemisphere, going down to mid-latitudes, okay, as far south as 38 degrees north, which is the latitude of Athens on Earth. Okay, so these glaciers are not confined just to the poles. These glaciers are they're south of you, okay, and these are pure water ice covered by a few meters at most east. So they are within shovel distance of the surface. They are a massive resource. The amount that's been discovered is on the order of 1 million cubic kilometers, which is about the amount of fresh water there is in Europe. Okay, just in these pictures. There you have it. So now, these developments, Kepler, Reconnaissance Orbiter, the Mars Express, various Curiosity, these are the accomplishments of the established space program. NASA, ESA, so forth. So they actually have been doing epic work in the areas of robotic planetary exploration and space astronomy. They have not been doing so well in the area of human exploration. In fact, they haven't been doing well at all. Aside from supporting the operation of the Hubble Space Telescope, which NASA astronauts did do and played a critical role in, I would argue the human space exploration program has not accomplished anything in half a century. Well, in 47. And that's because it's operating without direction. That is, while the robotic planetary exploration program is operating as a purpose-driven program, it has real science goals, it seeks to pursue them at minimum cost, maximum science return. The human spaceflight program is really operating not as a purpose-driven program, but as a vendor-driven program, as a mechanism for distributing funds to various vendors and constituencies, and it has lacked drive. However, precisely this failure has created both a need and an opening for a new class of players in the space game, which is entrepreneurial space companies. No one was looking to private entrepreneurs to get us into space in the 1960s. NASA was storming heaven. Soviets were storming heaven. There was no need for entrepreneurial startups to be in the game then. But given the entropy, there has been need, and they have finally stepped up to the plate. And in particular, SpaceX has proven that it is possible for an entrepreneurial space venture to do things that previously was thought that only the governments of major nations could do. And not only that, do them in a third the time, at 1/10 the cost, and even do things that the established space programs had deemed impossible, like having reusable rockets that land back at the pad. I don't know if you saw the photograph of the recent landing of a SpaceX booster at Vandenberg base in California, but the landing took place less than a kilometer away from the takeoff. Seen in two places. And amazing. And now they are moving on creating, a reusable heavy lift booster. BFR, I have some reservations about the way SpaceX claims it wants to use BFR. It does refuel it on orbit, fly all the way to Mars, refuel it on the surface of Mars, fly all the way home. I think, just based on simply proper use of capital, they should not send it to Mars and back. You can either send it to Earth orbit and back, and now you have a fully reusable heavy lift launch vehicle, 150 tons to orbit. There's no arguing with that. Or if you can refuel it on orbit, just have it go out to about translunar injection, that is a trajectory where it boosts things to the velocity just short of Earth escape, and have it loop back to Earth orbit and be home in a week, instead of going to Mars and back, in which case it won't be back for 2.5 years. And since launch windows to Mars will be for 2 years, it means you won't get to use it, except once every 40 years, which is ways. Just go to orbit with it, and use it every day. If you go to translunar, you can use it every week. But even so, there it is. Heavy lift is on the way. Semi-heavy lift is already a reality. Falcon Heavy. about half of a true head-on booster. 60 tons to orbit kind of booster instead of 120 more. New Glenn. Bezos is in the game, and I think, well, it is the case that Musk has not only accomplished certain things of his own, important things, he has made this demonstration of the potential of private space companies and thereby enabled a lot of other private space companies to get funded. There's 3 serious small launch vehicle companies that I'm acquainted with, Vector Space, Firefly, Electron, that have gotten funding now in the $100 million class. And they're on their way, and there are probably others that I'm not acquainted with, because some stuff is going on that's not. And I'm convinced that within 5 years there'll be at least 10 SpaceXs in the world, that is SpaceX type companies in various nations. I'm hoping there's one here in France. That's up to you to make happen, but there's no reason why it can't. And this is on the way. And these companies competing with each other will drive down the cost of space launch. Musk already has significantly. That is, previous to Musk, the cost to launch to orbit was $10,000 a kilogram. Falcon Heavy's now offering launch at $2,000 a kilogram. That's a factor of 5 reduction. And if they get some other players in the game, it'll be driven down even more. I believe potentially it can be driven down as low as $200 a kilogram. Yeah. And that would make it possible to go to space for the same price as a first-class ticket from Paris to Australia. Not as cheap as the Metro, but still, it's a number that would make interplanetary colonization possible. So, however, it has to be said that, well, first of all, if you're up for it, if you have either the technical smarts or the business smarts or the networking smarts, I would suggest that you might want to get involved with creating a space company of your own. And it could be a launch vehicle company, it could be a spacecraft company, it could be an instrumentation company. There's all sorts of parts of this business that are open. Okay, it's not just launches, which tends to be the most capital intensive part. But there's other parts. But if not, there's a role for everyone. Because the Musks of the world will still need help from the public if they're going to open up the space frontier. We have to have a purpose-driven space program. You know, right now, I mean, I believe it is actually a scandal that the space programs first said, well, before we go to Mars, we have to go to the moon, because going to Mars is hard, and then say, well, we're not ready to go to the moon, so we're going to put a space station over the moon. Now, which they call the Deep Space Gateway. I call it the Lunar Orbit Toll Booth. It is not necessary to have a space station in orbit around the moon to go to the moon or to Mars. And furthermore, if you had one, it would place a requirement on the missions to use it, because believe me, the bureaucrats do not want to build a station and then see you go to Mars without stopping there, because that would make it apparent that the station had no purpose, which is the truth. You know, Trump just criticized the assassination of this Saudi character by saying this was the most incompetent cover-up in history. Right, so why couldn't they do a competent cover-up? Okay. Well, the people who create this station aren't going to want to have you reveal the fact that the station has no purpose. So you're going to have to go there, which will make the missions much harder. It will add to the propulsion requirements, it will add to the timing requirements to have to phase and rendezvous with these stations. The analogy I use for the lunar orbit toll booth is this. Let me offer you a business deal. I want to rent you an office in Saskatoon, Canada. Have you been to Saskatoon? Okay, it's not that popular tourist destination, but it's there. And so here's the deal. You have to pay for building the building. You have to pay $100,000 a month rent, 30-year lease, no escape clause. You must spend at least a month every year in Saskatoon, okay? And if you want to fly anywhere, you must stop there on the way from now on. That's the lunar orbit toll booth. All right, so how can you have a program that is so misdirected? It's because it has no direction. And sure, if that's the program, then Musk and Bezos will build vehicles that deliver cargoes there and people there and so forth. But you won't get to the moon, let alone Mars. So if we want these new, cheaper, better space capabilities the entrepreneurs are developing to actually lead to the settlement of the moon and Mars, we must insist on a purpose-driven space program. And so I'm going to show you right now how I think it can be done. That is why we do not need, I mean, the Mars plan of NASA involves building giant interplanetary electric propulsion spaceships that will never be built and therefore will never fail. I want to show how this can be done, just simply from an engineering point of view, and then you can see how we could readily take advantage of, for instance, the BFR or even the Falcon Heavy or comparable launch vehicles that that will exist shortly to actually do this. That this is not something that needs to be done by, you know, our grandchildren. This is something we can do. That is, the first people to land on Mars should not be people who haven't been born yet, but people who are astronauts today. So, all right, so again, here's a NASA concept for the first human mission to Mars. Okay, it's modeled on the Imperial Star Destroyer. You see? So it has heritage. It's fairly large. Mars is here for scale. Okay, if this is how we're going to Mars, we're not going to Mars. Okay. They say we need to go to the moon before we go to Mars in order to practice. Well, practice is a good thing, but we can practice on Earth. Okay. There's two people in this room that has been here. There's one, there's the other. But this is the Mars Society's practice Mars station, the Flashline Mars Arctic Research Station. We are able to do that now. Okay, and if NASA was serious about the moon and Mars, they would have several of these stations built at a higher level of fidelity than we can with our resources, and they'd be practicing now, instead of saying practice is something we need to do, but not do. But they're not doing it. Okay. All right. We do need heavy lift. The heavy lift is not science fiction. This is Saturn V. This is 1969 we're looking at here. Not only are we about to have Saturn V capability, which is what SLS does represent, but we're about to have reusable Saturn V capability, which is what BFR represents. And if you have such capability, and here's how you might do a Mars mission. Once again, no Star Destroyers required. You can launch to Mars every 2 years. Year 1 is the first year of flight operations. You launch 1 heavy lift booster or its equivalent, and you use its upper stage to throw an unmanned payload, automated payload, to Mars. This is flying on a minimum energy trajectory. It takes 8 months to fly to Mars. Not that long. Okay. Flies to Mars, then it uses an aeroshield to capture into orbit around Mars. And then after we make sure it's in good shape and the weather is clear, we bring it into the atmosphere deeper, use the aeroshield to slow down to subsonic speeds, then we pop a parachute, come down slow, and put ourselves down softly on the surface of Mars, just like we did with the Viking mission in 1976. What happened when we were on Mars? The main object is the Earth Return Vehicle, or ERV. This is a little rocket ship for flying back from Mars to Earth. There's no one in it though. It's got a cabin suitable for 4 people, 5.5 meters, 5 meters, enough space for 4 people, 2 decks. Then we have 2 methane oxygen rocket propulsion stages here, which however are unfueled. Okay. And on the first mission, we fly it out, however, with 6 tons of hydrogen in its lower stage tanks. And then slung below the vehicle, we have a robotic rover resembling a small pickup truck. And in the back of the truck, we have a small nuclear reactor with a power of 100 kilowatts. So this is not like a big nuclear power plant that powers a city, which might be 1,000 megawatts. This is 100 kilowatts. It's about the same amount of power that powers a mid-sized car in America. So it's not a huge city powering plant, just a nice little putt-putt nuke sitting in the back of the truck. And then after we've landed it, we telerobotically drive the truck a few hundred meters away from the landing site, unwinding a cable off the back of it as it goes. And then when it gets a suitable distance away, the reactor is lowered off the truck, is put on the ground, preferably in a depression in the terrain like a crater, and then we turn the reactor on, and now we have power here. And what we do is we run a pump, and we suck in the Martian air, which is 95% carbon dioxide gas. A lot of people complain about carbon dioxide, but it has its uses. And plants use it, and also you can use it to make fuel with, okay? You brought some hydrogen to Mars. Later missions, once we're established there, we'll probably make use of Martian water, because now we know the water is there. But probably on the first mission, we don't want to have to mess with that, especially since there's no people there. We just want to use the simplest method of feedstock acquisition, is just running a pump to suck in the Martian air. Okay, you can't mess with that. Carbon dioxide can be reacted with hydrogen. In the presence of a catalyst, produces methane and water. This is known as a Sabatier reaction. Okay, after a person from a certain country that Paris is the capital of, who did this in the gaslight era. Okay, methane is a good fuel. That's the fuel for the rocket to come home. The water is electrolyzed, is split into hydrogen and oxygen. Oxygen is the oxidizer to burn the fuel. The hydrogen is recycled to do this again. And then to make enough oxygen for the right mixture ratio, we have a third reactor in which we split carbon dioxide into carbon monoxide and oxygen. Oxygen, we keep carbon monoxide, we vent as waste. You can do that as on Mars. There's no EPA there. And in fact, NASA is going to do this on Mars in the Mars 2020 rover. They have an experiment where they will demonstrate this reaction. So this is we're going to do it. Okay. And when you're all done, you've taken the 6 tons of hydrogen you brought from Earth, or the no tons of hydrogen you brought from Earth once you start using Martian water. Okay. And you've turned it into 108 tons of methane oxygen propellant on the surface of Mars. So even when you have to bring the hydrogen, you're getting 18 times as much propellant as what you're bringing. Okay? That's like a pioneer acquiring the useful mass of a bison for the transported mass of several bullets and cartridges. And that's what makes the whole mission sing. We're using the resources that are available on Mars. This has been the key to successful exploration everywhere on Earth. Use the resources in the environment you intend to operate in. Okay? And so, in fact, we make so much propellant, we make more than what the Earth return vehicle needs. We have 10 extra tons that we can use to power ground vehicles that run on methane oxygen propellant. And that's a really good thing, because why are we going to Mars? We're going to Mars to explore. What's the number one requirement for exploration is mobility, okay? And chemical-powered vehicles have much higher power-to-mass ratios than you can get with electric vehicles. And on Mars, in a frontier environment like Mars, you really do need the range, the muscle, the speed that you get from having a real car instead of a golf cart. So you want to have it. But you wouldn't be able to do that if you had to bring the propellant from Earth. But since you can make it on Mars, you can. And so that's another important point. The ability to make use of Martian resources is not only the key to making the mission cheap, it's also the key to making the mission effective. And that's equally important, because there's no point going to Mars unless you can do something useful when you get there. So, it took 8 months to fly to Mars, 10 months to make the propellant. There's 26 months in between launch windows. So long before the next launch window opens up, we will know we have a fully fueled Earth return vehicle sitting waiting for us on the surface of Mars. That being the case, at the next launch window, we launch 2 more payloads to Mars. Another one of them is another Earth return vehicle. The other is a habitat with a crew of 4 astronauts in it. Now, because our ride is waiting for us on the surface of Mars, we don't need to fly to Mars in an Imperial Star Destroyer. We don't even need to fly to Mars in a comparatively modest Millennium Falcon. No, we can fly to Mars in a tuna can. Now, this is somewhat larger than the tuna can you get at the grocery store. This is 8 meters in diameter and about 6 meters tall, so it's got 2 decks, each with 3 meters of headroom. Okay, the upper deck is where the crew really lives. The lower deck is more of a garage, workhouse, workshop, and storage area kind of place. Here's one potential layout of the upper deck of the HAM. You see there's a little stateroom here for each of the 4 astronauts. Toilet, science area, exercise area, and the galley wardroom, kitchen table. And in the center, what you see here is what's called a solar flare storm shelter. Okay, now this is worth talking about for a minute. There's 2 kinds of radiation that can get you in interplanetary space. There's solar flares and there's cosmic rays. They are entirely different in character, they are entirely different in origin. Solar flares come from the sun, okay? Le flare solaire. And did I get that right? Close. Anyway, and they're major events where the sun shoots out a lot of radiation, and over the course of 3, 4, 6 hours, it puts out enough radiation that can deliver about 10 sieverts worth of radiation, 1,000 rems, to an unshielded astronaut, which is enough to kill, either immediately or after a fairly brief period of radiation sickness. That's the bad news. The good news, however, and you might get one of these flares about once a year, and there's a high probability there that we might get one because We're going to be taking 6 months to go to Mars and 6 months coming back. It's a year in space. So there's a good chance there'll be a polar solar flare while we're in transit. But the good news is the kind of radiation that solar flares are made of are just protons with energies of about 1 million volts. And they can be stopped by 10 or 12 centimeters of water. Or things that, from a nuclear point of view, are essentially the same thing as water, such as food. Or things that water and food become as the mission proceeds. And we have enough of that material on board to pack it in around a small part of the ship. So this is shielded with more than 12 centimeters worth of water. So this is the pantry storm shelter. A solar flare happens, the alarm rings, the crew goes in here, and they're huddled pretty tight, okay, for a few hours until the all clear rings and they come out. And that's how they're safe from solar flares. Okay. We didn't bother with that during Apollo because those were only 1-week missions and there was a very low chance there'd be a solar flare during that time. Also, we didn't have enough mass. The amount of supplies on the Apollo mission was low because the mission was only at most 2 weeks long. Here, this is a 2-year mission. We have enough supplies to create a shield. Now, the other kind of radiation is different. This is cosmic rays. And they don't come from the sun. They come into our solar system from interstellar space. It's not clear what their origin is. We don't really understand how they're created. There's no physics that can properly explain it. But nevertheless, it's quite true that they're there. They are particles that are coming into our solar system, not with energies of millions of volts, which are the typical energies of nuclear reactions, fission and fusion. So we can explain solar flare energies easily. Cosmic rays, they come in with energies of billions of volts. That is 1,000 times more energy than a solar flare particle. 1,000 times more energy, particle for particle, than you can get from a typical nuclear reaction. So you can't stop that with 10 centimeters of water. You need meters of water to stop that. And we don't have enough mass on the ship to do that. We can't. So you're going to take the dose. But the good news is that the dose is not that large. It's around half a sievert, 50 rem, for every year you're in interplanetary space. And it's fairly predictable. It's not like a solar flare where you get a big one every once in a while. It's just a constant little drizzle of radiation. And well, what is half a sievert worth of dose delivered over a long period of time, over about 2 years? What does that mean? It represents about a 1% risk of getting a fatal cancer at some time later in life to a 35-year-old woman. Okay? Slightly lower risk for a man because it doesn't have the risk of breast cancer. Lower risk if you're older, because older people are actually more resistant to radiation-induced cancer, and also they have less time to get cancer. Okay? Somewhat larger risk if you're young. But in simple terms, it's about 0.5% risk of you're going to get cancer, assuming no advance in medicine. That is actually a modest part of total mission risk. If you consider the shuttle, its actual risk that you would get killed flying the shuttle was 2%. And not later in life, but during the mission. Okay. And yet, how many of you were given a chance to ride the shuttle? I'm there. Okay. And a Mars mission has to be riskier than a shuttle mission because it's not just a launch. It's from Earth. It's travel through space, landing on Mars, operations on Mars, takeoff from Mars, and re-entry to Earth. So it's a modest portion of overall mission risk. Furthermore, a lot of people have already encountered it. That is, the cosmic ray dose rate in interplanetary space is only a factor of 2 more than what we see at the space station. Because the Earth's magnetic field does not black out these billion-volt particles. It can't. It's too weak. The space station is shielded by having the Earth on one side of it. That blocks out half of all possible angles of approach. But for the rest, it's open. So you have people who have spent time either in the space station or Mir, or both. Many of them have gotten cosmic ray doses comparable to what they would have gotten on a Mars mission, and we see no radiological casualties among this group. Or put another way, if you're an average person living in an advanced country and you don't smoke, you have a 1% chance of dying of cancer. Excuse me, you have a 20% chance of dying of cancer if you're not a smoker. This would add between 0.5%, at most 1% to your risk. Make it 21 tops. If you're an average smoker, it's 40. So actually, if we recruited the crew out of smokers and sent them to Mars without their tobacco, we would be reducing their chance of getting Also, it must be said that, for instance, American astronauts, they live in Houston, where there's petrochemical fumes in the atmosphere, which are actually more carcinogenic than cosmic rays. So you'd also reduce their chance just by getting them out of town. Now, there is something that we have encountered in space that has received less attention. People tend to get very tight about radiation, but the thing that has actually caused damage to astronauts' health is not radiation. It is zero gravity. Okay. Zero gravity causes deterioration of bone and muscle, and also nausea in some cases, and distortion of vision and other things. So while you certainly can survive 6 months in zero gravity, and that's how long we're going to be in space on the way to Mars, in 6 months. There, we're going to travel a little faster than minimum energy to get to Mars. And 6 months is the standard duration of a space station rotation. Nevertheless, we don't want the crew arriving on Mars weaker, because they're going there to explore, and exploring field exploration is like heavy-duty backpacking. And so to do it effectively, you want the people in good physical shape when they get there. So I recommend that we do artificial gravity. You can make artificial gravity by spinning a spacecraft. The longer the swing arm, the slower you spin it, the less secondary effects, Coriolis effects there are. So I think the simplest way to do it, and have a long swing arm, is just tether the spacecraft off the upper stage of the booster. This is the booster that threw us from low Earth orbit onto a trans-Mars trajectory. So it's coming along for the ride. We can tether off of it. This is about 1.5 kilometers long. Spin this up at 1 revolution per minute, we create Mars gravity in half. If we spin it at a little less than 2 revolutions per minute, we can create Earth gravity in half. And that's how we avoid the health effects of zero gravity. All right. So, they took 6 months to go to Mars. And by the way, let me just tell you, there are people that say, well, we have to go to Mars faster than 6 months. Well, first of all, we can go to Mars in 6 months. In fact, the InSight probe that is on its way to Mars right now was launched in May. It's going to land in November. That's the 5th month to the 11th month. That's 6 months. Okay, so this is not, we're not talking about the future here. We're doing this year. And in fact, the European Mars Express orbiter got to Mars in just about 6 months back in 2003. So we can get to Mars in 6 months. Anyway, when we get close to Mars, we fire a pyrotechnic device that cuts this cable. They go and they aerobrake into Mars orbit. And then after we check them out, check out the weather, we go and land at landing site number 1, with a fully fueled Earth return vehicle is waiting for them. Now this thing's been on the ground on Mars for 2 years. We have thoroughly explored the locality with robotic rovers. We have, and given photographs to the crew so they can train. There's a radar beacon to draw them in. There's an expert pilot flying this. We should be able to land right on this one. And some of you may remember, and others may have read, that during the Apollo program, we actually landed an Apollo lunar lander within 200 meters of a Surveyor spacecraft that had been landed on the moon before. And we had better guidance systems now. So we should be able to do it. But let's say we land 20 kilometers away. That'd be a big one. Or 50 or 100. We're still fine. Because we have with us in the lower deck of the hamp a pressurized ground roving vehicle. It runs on a methane oxygen engine and has a one-way driving range of 1,000 kilometers. So it would really take, did I say 1,000? I believe it's 600. Okay. Even so, if you can't land within 600 kilometers, you shouldn't be on this mission. And the agency that is sending you there needs different people doing pilot selection. That's another problem. Okay. So let's say, however, that does happen and you land over here on the wrong side of the planet. You're still okay, because we got the second Earth return vehicle following us out to Mars, and if we land on the wrong side of the planet, we bring this down to land near us wherever we go. Now, in that case, we would be depending upon the chemical synthesis to work in real time instead of having done this work before we even launched. But the success of the technology has already been proven by the success of the first one, and we do have a human crew on the scene assisting chemical synthesis operation should it malfunction while they are there, although in this particular example, you would not want the pilot participating in that. But, so it's pretty good third level backup. And finally, as a fourth level backup, if we can't land accurately, if we can't drive there, if we can't use the second Earth return vehicle, as a fourth level backup, we've got the whole crew landed on Mars, where they have natural gravity, they have substantial radiation protection offered from the Martian environment, and enough supplies with them to last for 2 years for the next launch window to open up, and more supplies and another Earth return vehicle sent out to them at that time. So we have a 4-layer defense of the mission, and each layer involves actually carrying off the mission. But let's say it works the way it should. We land, and here, we already had automated health checkout on this vehicle. Now we can go and examine it manually. It's fine. We don't need this other Earth return vehicle. We landed somewhere else where it will make propellant to support the next human mission that flies there, along with another Earth return vehicle, which is their backup, but which otherwise opens up site number 3. So the idea is every 2 years you're launching 2 boosters. One to send out an Earth return vehicle to open up a new site, the other to send out a crew to exploit the previously open site. 2 boosters every 2 years. That's an average of 1 per year. When we were launching space shuttles in a serious way, we were launching 6 a year. So we're talking about using 16% of our heavy lift capability to support the human exploration of Mars. It means we could do the moon at the same time. So there is not a conflict here of moon and Mars. There's only a conflict if someone is trying to avoid going to Mars and is saying, oh, we need to just do the moon first for some decades. And then they say, but actually we're not ready to go to the moon, so we're going to do a lunar orbit space station. And then as soon as you agree to that, they'll do a space station that's halfway to the moon. Yeah, right. So, there's no conflict. We can do the moon and Mars at the same time. So this is an actual photograph of Mars. So here is the Earth return vehicle. Okay, the cabin, the 2 propulsion stages, the chemical plant in the landing stage. Here's the reactor providing the power so that these pumps can suck in the Martian air and do chemical synthesis. Here's the habitat module, upper deck for habitation, lower deck is the garage, a little pressurized vehicle. Some solar panels to set up to use as backup power if we have to turn the reactor off for any reason. We also have backup power from the engine of the car. And also, this is the light truck over here, probably hard for you to see, but it's an unpressurized vehicle that can also generate power. It's also a backup vehicle for that. This is an inflatable greenhouse. This is not a mission-critical element. It's an experiment in learning how to grow crops on Mars, in Martian soil, Martian water, Martian gravity, Martian sunlight, for the benefit of future missions and future bases. Now, we're going to be on Mars for a year and a half. Why a year and a half? Because that's how long it takes for the planets to move around to give you the proper launch window back to Earth. There's an alternative plan where you leave after 1 month, but then you have to spend almost 2 years in space. And so I don't think that's an intelligent plan. This plan, you only spend 1 year in space, but you spend a year and a half on Mars instead of 1 month. Because the time on Mars is productive time. The time spent in space is not productive, and it just adds to radiation exposure. Okay. On Mars, you have substantial radiation protection, offered first of all by having Mars under you, second of all having the Martian atmosphere. Now the Martian atmosphere is very thin, only 1% as thick as the Earth. But if you're looking straight up like this to the zenith, there's the equivalent of 16 grams of water, 16 centimeters of water between you and straight up. Okay. However, most particles don't come straight down. They come like this. And if you average the atmosphere over the hemisphere of the sky, it averages to 65 centimeters of water, 2/3 of a meter, which is substantial. So you reduce cosmic rays and you completely shield out solar flares. Okay. And as far as the zenith is concerned, you can shield that just by putting sandbags on the roof of the hat. Anyway, we're on Mars for a year and a half. We're going to explore. What are we going to explore for? Well, there's all sorts of scientific questions, and there's all sorts of scientists that want to do seismology and meteorology and this and that and the other thing, mineralogy, and they're all entitled to get papers published so they can get tenure at universities and put their children through college. But there are two scientific questions that make Mars of interest, not just to professors wanting to make publications, but to all of humanity. And these questions revolve around life. The first set of questions revolve around the issue of was there or is there life on Mars? Okay, now see here, this is a real photograph taken by the Viking orbiter in 1976, and what you can clearly see here are water erosion features. You don't see anything like this on the moon. There's no water erosion features on the moon. There's thousands of them on Mars, thousands. Okay, dry riverbeds, dry lake beds, dry ponds. Okay, and since this photograph was taken, we landed rovers on Mars that have found salt deposits left by retreating waters, and there was water on Mars, lots of water, and now we've even found places where there still is liquid water underground on Mars. So, the question is this. Current theory is that life evolves from chemistry, where you have liquid water, appropriate minerals, sunlight, and a given amount of time, that it is a natural development from chemistry. It does not require divine intervention, okay? And if that is true, then life should have appeared on Mars, okay? Even if it subsequently went extinct when the surface deteriorated and no longer had liquid water, there should have been life on the surface for some, because there was not only liquid water on Mars, there was liquid water on the surface of Mars for 1 billion years, which is 5 times as long as it took life to appear on Earth after there was liquid water here. So if the theory is correct, that life is a naturally emergent phenomenon from chemistry, life should have appeared on Mars. And we should be able to go there and at least find fossils. Okay. Now furthermore, we now know that there is liquid water underground on Mars. Okay. Go there and drill, bring up samples of that water. If there was ever life on the surface of Mars and the surface became uninhabitable, the life would have retreated into the places that remained habitable, which is to say the groundwater. This, in fact, is what happened on Earth. You know, our kind of folks are not the original inhabitants of the Earth. The original inhabitants of the Earth were microorganisms that could not tolerate oxygen in the atmosphere, because the early Earth had no oxygen. Oxygen is an artifact of photosynthesis. Plants, when they developed photosynthesis, started putting oxygen in the atmosphere, eventually making the surface uninhabitable for most of the original microorganisms. So they retreated into the groundwater 3 billion years ago. They're still there today. And they've seen stuff up above them come and go. You know, the trilobites have come and gone, the dinosaurs have come and gone, the mastodons, the Wehrmacht, you know, they've seen them come, they've seen them go. Okay, and long after we're gone, they'll still be there. Okay, if there was ever life on the surface of Mars, it's in that groundwater. And if we can go there and sample it, we could see what it is like. And if it is the same as Earth life, or if it is something different. You see, all Earth life, even those original inhabitants that couldn't tolerate oxygen, are all the same at the biochemical level. They all use DNA and RNA. That is, they all use exactly the same alphabet for communicating genetic information. It's a very elaborate alphabet. Okay, now, okay, you, French, me, English speaker, we use the same alphabet. Okay, and there's several other countries that also use the Latin alphabet. But, you know, if you go 1,000 kilometers east of here, you'll start running into people that use a different alphabet, Cyrillic alphabet. Okay. Well, there is a common origin between the Cyrillic alphabet and the Latin alphabet. They share some letters and certain basic principles of communication. But if you go to certain other countries, China, there's a totally different alphabet that doesn't work on the same principles at all. Okay, it doesn't have a common origin within the Latin alphabet. Okay, so does life on Mars use the Latin alphabet? Or does it use a Phoenician alphabet that was an ancestor of both the Latin and the Cyrillic and the Hebrew alphabets? Or does it use the Chinese alphabet? Okay. Or one of these other Asian kind of alphabets that are totally different in origin and principles than the European alphabets. This is fundamental. Okay. So, in other words, is life as we know it what life is? Or are we just one peculiar example drawn from a much vaster tapestry of possibilities? This is worth finding out. And you're only going to find this out with people. I mean, even fossil hunting involves hiking long distances through unimproved terrain, you know, doing heavy work, digging, pickaxe work, doing delicate work, carefully breaking open fossil shales, pry apart the pages of rocks that have been pasted together. You know, that's way beyond the ability of robotic rovers. And drilling and bringing up water samples and culturing them in a laboratory and subjecting them to biochemical tests and so forth to see if they're DNA and RNA, or if they're different, and if different, how different. Okay? This is way beyond robotic rovers. So if we want to know the truth about the potential existence, prevalence, and diversity of life in the universe, we need to go. That's all there is to it. And I must add, there's these people running around now saying, well, we can't go, because if we did, we won't know if the life we find there is native or if we brought it. Okay? Well, I had the same problem coming to France. I didn't really know if there were people native to France. You guys could have all gotten off the plane at the same time I did. But I was able to resolve this because I found structures here in Paris that were not built today. Okay? In other words, I found evidence of the past existence of the French. Okay? Really, I did. And so if there's life on Mars and it's native, there will be evidence. It was there before you got there. There'll be biomarkers from yesterday. There will be fossils from 1,000 years ago and 1,000,000 years ago and 1 billion years ago. And unless you're one of these people that believe the fossil record on Earth doesn't prove anything, that God could have put the fossils in the ground to fool us into thinking that there was a geologic past, when really the Earth was created in 7 days, 4,000 years ago. Unless you're on board with that, you got to know that if you find life on Mars, if it's native, there will be evidence of its existence in the past. Now, in addition, there could be additional evidence, because if it's different from Earth life, fundamentally, if it uses a different alphabet, or even if it simply has a form that is something we've never seen before, then you also know it's not native. But if all you find are familiar types of bacteria, and you find no evidence that they existed in the past on Mars, then yeah, you brought them. It's that simple, okay? But there it is. So if we go, we will know. If we don't go, we're not going to know. Okay. Now, at the end of a year and a half, we get in the Earth return vehicle. We start it up, we take off, we fly it back to Earth. We leave the ham behind on Mars, the reactor, the truck, etc. All this stuff, we don't need to bring it back to Earth. We have a lot of stuff here already. The idea of Mars missions is to go to Mars with as much stuff as you can and come back with as little as you can. Because everything you leave behind is available for the use of future missions. Okay? So here's a map of Mars. Texas is here for scale. Okay? And you can see that after 8 missions have happened, we will have relocated Texas to Mars. What you will have done is each of the circles, okay, it has a radius of 600 kilometers, 300 kilometers, has a radius of 300 kilometers, a diameter of 600 kilometers. It's about the size of Texas. So this is what one mission can explore. It can also drive from one center to another, and so you keep exploring other places. But after a number of these missions have occurred, we're going to know the answer of whether there was ever life on Mars, whether there is life on Mars, whether it uses the same genetic alphabet as us, or whether it's different. We're going to know that. And now the question about Mars is going to shift, okay, to a different question, which is, will there be life on Mars? Okay, because, look, the most important thing to know about Mars is this, that Mars is not just an object of scientific inquiry. It is that, it's the Rosetta Stone for letting us know the truth about the prevalence and diversity of life in the universe. But it's something more important than that. It's a world. It's a world. It's a planet that has a surface area equal to all the continents of the Earth put together, that has on it all the materials needed to support life and therefore civilization. And if we can go to Mars and learn how to use these materials, through that knowledge we transform these from being mere materials into being resources. There is no such thing as a natural resource. There's only natural raw material. Okay? It is human ingenuity, creativity that turns materials into resources. You think of land as a resource. No. Land is just something that was there. Until we invented agriculture, land was not a resource. It was just something you had to travel over to try to catch deer. Okay? Something got in your way. But through agriculture, we turn land into a resource, a very valuable resource, and through advancing agriculture, we multiply the value and magnitude of that resource. Okay? Oil was not a resource until we invented oil drilling and refining and machines that could run on the product. Uranium was not a resource until we developed nuclear power. Deuterium is not a resource now, but it could be if we develop fusion power. Okay? And Mars is not a resource now, but it will be once there are smart people there who are resourceful and therefore figure out how to use Martian materials to make useful things. And so if we can go there and do that, if we can go beyond the Mars direct stage, which uses Martian materials to make fuel and oxygen, if we want to learn how to grow food on Mars, learn how to extract water from glaciers and from subsurface reservoirs, if we learn how to extract power from geothermally heated subsurface reservoirs, if we learn how to make bricks and ceramics and glasses and plastics and metals and wires and tubes and habitation structure, if we go up this chain of craft, okay, we can develop the technologies that turn all sorts of things on Mars into resources, and so the planet becomes a place that human beings can settle. And in short, in the fullness of time, we can make Mars habitable. Now, what do I mean by make Mars habitable? Do I mean terraform the planet? You know, like in Star Trek II, the Revenge of Khan, where they throw this thing down on the planet and the Genesis machine and turns the planet into a fully living world covered with forests and meadows and flowers and chipmunks and butterflies and flying fish. Will we do that to Mars? Is that what I'm saying? Yes, that's exactly what I'm saying. Yeah, I think we're going to do that someday, because we're life, and it is the basic principle of life to take barren environments and transform them into places that are friendly, that are fertile, that support the development and propagation of life. It is because of that that life on Earth has been successful. Life has transformed the Earth. The Earth today is a much more favorable place for life than it was when life got started here. Okay? And no sooner does any barren place appear on the Earth than life transforms it. Okay, think of Hawaii coming out of the Pacific Ocean. New land, we were born out of the ocean. Is it friendly to life? No, it's barren basalt. But then birds fly over, they drop seeds, the place becomes lush, Polynesians show up, let loose pigs, so something good to eat, Europeans show up, build first-class hotels, so there's a nice place to check in. This is what we do, okay? It's what we do. And it would be unnatural, literally unnatural, if human beings, as the kind of bird this biosphere has evolved to carry its seeds elsewhere, did not do exactly that. So we're going to do that someday. But that's not what we who are in this room tonight are going to do. Because that's a little beyond our time. However, we can transform the planet in a different sense by transforming it intellectually, by developing the crafts, the technologies that make it habitable, and therefore, in the fullness of time, it settled. Okay, I think that, I was asked this question on the radio show today, caller calls in and says, you have these entrepreneurs going there, they're going to set up their own governments on Mars. We won't have the law and order from the US government, and all these people just going there setting up any old government they want. I said, that's the idea. Okay, that is the idea. That is really what is beautiful about the current situation. Okay, you might be thinking about having this government set up governments on Mars, but we're going to have hundreds ultimately of settlements on Mars, hundreds of city-states, and they're going to be founded by people with a variety of ideas of how society should be organized. Some might be socialist, some might be free enterprise, some might, you know, have all sorts of ideas, and these will be experiments. Okay, they're not going to be set up to be experiments, but they will be experiments. They will be noble experiments, and the ones that work, the ones that provide people with a better way to develop and express their human potential, that provide a better life, immigrants will go there. Those that are oppressive, immigrants will not go there, and those settlements will fade and die. Okay? But the ones that show a better way will grow, and they will be copied. And this is how Mars will be settled, and this is how it will contribute to human progress on Earth. Not just through the technologies that will be developed on Mars, because they're going to face all sorts of novel challenges that they'll have to resolve to be able to develop, and some of those technologies will be licensable on Earth. For instance, ultra-productive crops, because their greenhouse agriculture is going to have much more limited land than Earth will, so they'll be into genetic engineering, they'll develop new crop strains, they can license those patents on Earth, create income, pay for imports. But the greatest export will be the noble experiments, the results of the noble experiment, okay? And there you go. And I think that, well, just to finish a few other points. You have this hardware, you can land halves on the moon. We can do moon missions, you know, land halves on the moon, make use of lunar water to make propellant flying directly back from the surface. No lunar orbit space station and lunar orbit running can be required. Okay. So there's no conflict here. But this is the prospect that we have. If we have this entrepreneurial breakout going on, the kind of launch capabilities they're creating will enable these plans to be done. And once these plans are done, once we have these initial outposts on Mars, then it will be possible to think of establishing their own settlements on Mars. Because you see, there's nothing more valuable than freedom. And the ability to be able to go to some place where the rules haven't been written yet, write your own rules, make your own world, that is a fundamental and grand form of freedom. And it's not just beneficial to the people that exercise it, it's beneficial to everyone else. Because we get to see the results. And so, in short, I don't think we're living at the end of history. I think we're living at the beginning of history. That if you know, future ages looking back at this time, you know, they're not going to be interested in how Brexit turned out, or the results of the Mueller investigation, or which gang of thugs won in Syria. Okay, but they'll be living on thousands, not only in hundreds of Mars city-states and asteroidal city-states, but on thousands of planets orbiting stars in this part of the galaxy. And when they look back at this time, and to the extent they have any appreciation of the difficulties that people in this day and age live on compared to the kind of lives that they will live, much more advanced technological societies. And I believe, in general, much happier societies, because they will be based on the knowledge that was gained in all these noble experiments. This is what they will consider important, that we set sail for other worlds. This time will be remembered because this is when we first set sail for other worlds. This is the beginning of history. And we have a unique chance, we who are alive today, in playing significant roles in making this happen. We can do something that's really going to matter, create something that is truly wonderful. And if you have it in your power to do something that will really matter and create something that is truly wonderful, then you should. All right? Thank you. To take questions. Sir? What is it?
Why doesn't have the Mars Society its own space program?
Well, okay. There are certainly people in the Mars Society who are engaged in technical work. That is of great significance. I myself, I have a company called Pioneer Astronautics. We develop new technologies for turning Martian materials into resources. Others are doing all sorts of things. But what the Mars Society is, although we do some research, we have our practice Mars stations, we're doing practice Mars missions, trying to learn what's going to work on Mars and what isn't. Our fundamental role, our most powerful role, is as spreaders of the idea. Okay, we do three things. One is talks like this, spread the vision. Second is political work, trying to defend various programs, political class, mind and race. And the third is our stations, where we do our own research. But I think that the first, which while least quantifiable in its results, is probably our most important work. Victor Hugo said, "Nothing can stop an idea whose time has come." And the reason why that is true is because an idea whose time has come has the capability of recruiting forces, potentially very powerful or even unlimited forces, to its banner to actualize it. And, I myself helped convince Elon Musk into making Mars his calling. Okay, so the Mars Society had a significant role in the creation of SpaceX, and there are many people at SpaceX and at Blue Origin who were recruited to this cause by the Mars Society. So that's our space program. Our space program is the people's space program. Our space program is, well, first of all, we do try to influence the government. I want people to put pressure on the governments to set meaningful objectives for their space program so that they can act as an effective partner and catalyst in enabling these private space launch companies and spacecraft companies from to get where they need to go. But also, if we could recruit, more Elon Musks, if we could recruit, well, we kind of recruited James Cameron, but he's yet to actually produce the movie. But, look, poet Percy Shelley said, "Poets are the legislators of mankind." In other words, ideas are upstream of politics. Okay, and so yes, we are trying to spread this vision. We're trying to get more people involved, whether as technical people, scientists, financiers, or poets. Because anything that anyone here can do directly to advance the cause of settlement of space, or indirectly by spreading the vision themselves in their own way. This is what we do. Sir?
Yeah, thank you for your presentation. In your opinion, why your vision has not been endorsed yet by space agencies or
Okay. All right.
Because it presents several advantages. Space agency and industry have different agendas, but
look, it's a pattern that many great enterprises start out as crusades and then become a business and perhaps eventually become a racket. These things happen. How many political parties that there have been that started out around a vision and then just became a political party interested in maintaining its power, okay, and lost sight of the vision for which it was created? All of them. And certainly bureaucracies get created. NASA was created as a crusade, storm heaven, and astonish the world with what free people can do, okay? And thereby contribute materially to winning the Cold War, and so forth, all that. Okay, once it had achieved that objective, okay, which it did. The politicians lost interest in it. NASA sought a way, well, some people left NASA. Others who that had become their life thought a way to, their goal at that point was no longer reaching the moon, it was preserving the agency. Shortly after I presented Mars Direct in 1990, the first time, which, by the way, had quite an effect, okay? We got a lot of support from within NASA, even from competing space companies. I was working for Martin Marietta, which subsequently became Lockheed Martin at the time, but there were even people at Boeing and elsewhere who came out in support. We want to get to Mars, this is it. Okay, but also we got a lot of opposition from the bureaucracy, and I was approached by a high-level NASA person who said, look, Bob, this is a really good plan, but you got to understand things. The last thing NASA wants is to get to Mars in 10 years. Job's done, go home. Okay, so for the NASA leadership, preserving the agency became the paramount goal. Now what about the political class? Because frankly, NASA never would have gotten to the moon in the 1960s unless they had been stuck with a very forceful imperative from John F. Kennedy. This is what you're going to do, okay? And then once that happened, certain people in NASA went along with it, others got out, and people who really wanted to do stuff like that got in, okay? But the American political class, and I think we're unique in this, has degenerated significantly since the 1960s. Okay, compare Trump to John F. Kennedy. Compare Macron to Charles de Gaulle. Okay, so don't laugh, right? The people that got us to the moon in the 1960s were the same people, or the younger brothers of the people that had won World War II. Okay, and done other massive projects, built the interstate highway system in the United States, which is an incredible thing, all sorts of stuff, okay? I mean, it's not just Trump. Obama got $1 trillion for infrastructure programs. They could have built intercity rapid trains in the United States. Nothing was built. They got tied up in their own red tape. So, so the quality of the political classes generated both in vision, in public spirit, and willingness to put country in front of party to accomplish bold endeavors and great projects. So you have deterioration in NASA, you have deterioration in the political class. But you do have some other stuff, okay? You had the growth of a vision. You had people who are now billionaires who grew up watching Star Trek. Say, how do we make this happen? In other words, the science fiction writers spread this vision. And, Musk, according to Forbes magazine, he's the 94th richest person in the world. He's not the richest person in the world. He's not one of the 10 richest people in the world. He's number 94. Okay? There's 93 people who got more money than him, and there are several hundred that have comparable money to him. Okay? Now, you have, with that many people with that kind of money, you have more chance of, a black swan. You understand what black swan is? This kind of unusual creature that pops up somehow. Musk's a black swan. Bezos is a very big black swan. 100 years ago, there were maybe 5 or 6 people in the United States as rich as Elon Musk. You can name them: Rockefeller, Harriman, Astor, Morgan. Now, who's the 50th richest person in the world? I don't know. Okay, never heard of so we have that, and then beyond the people who are actually that rich, there's millions of millionaires and 1 billion people on the planet who live well beyond the basic necessities. Okay, and So there's all sorts of ways this could be organized. It's conceivable, I mean, look, 1 billion people, I mean, in the advanced sector of the world, okay, let's say we get 10% of them, because most of them don't see it this way. Okay? A lot of people don't think space is important, but certainly at least 10% of people think that human expansion to space is important for the future of mankind. Okay, so that's 100 million people. 100 million people times $100 a year would be $10 billion a year for space settlement. That'd be enough to finally settle to Mars easily. Okay, so you can have that, or you can have this model that we're actually seeing right now, which is these entrepreneurs doing it. But the idea has recruited forces, and it's continuing to recruit forces. Intellectually, we're growing stronger, okay? And of course the technology, fundamental technology, is advancing as well. So this is going to be getting easier to do. At the same time, there's going to be more people and more money supporting the effort to do it. And I think, unless we have a major global disaster comparable to what happened in 1914, which throws everything off the rails, there's going to be the first humans on Mars by 2030, and there'll be human settlements on Mars in the decade or two after. And yeah, other questions? Sorry.
So for you, which will be the hard part? Will it be to go to Mars or to live on Mars for 1.5 years?
For me, I would say the trip is harder, and I'll tell you why. Because on the surface you get to do stuff, it's more fun. No, I mean, I'll tell you something. If you look at the human factors literature that was written prior to the activity of the Mars Society, various studies were done. What are going to be the human factors problem, the psychological problems of Mars missions? And they all say it's going to be boredom. Because their study populations have typically been people like US Navy personnel at the base in Antarctica. And these Navy enlisted men don't want to be in Antarctica. They want to be in San Diego, where there's Saturday night, the bars, the girls, the lights. Okay, that's where they want to be. They don't want to be in Antarctica. Okay, so they're bored. Okay, and you get all kinds of problems from them. Okay, we send a crew to Devon Island. Okay, or the desert station. If it's a good crew that is excited about the work and being in this incredibly strange place, the main problem we have is overwork. I led several crews in the desert and Devon Island, and I repeatedly had to order the crew to stop working at 9 o'clock at night. They burn themselves out. So if you send a crew to Mars that's actually interested in Mars, my objection to the movie The Martian, I thought it was a pretty good movie, but not a great movie. And the reason why it's not a great movie is because the character, the Matt Damon character, isn't interested in Mars. He just wants to go home. Why did he ever go? I mean, really. He's not interested in the search for life on Mars, and he's not interested in Mars as the new frontier. He just wants to get home. There's not one reflection he makes about Mars which shows any interest in Mars. You don't want to send that guy to Mars, okay? You want to send people to Mars that are interested.
So for you,
and then they'll have fun on Mars. You also want to send people to Mars that are fun to be with. Okay, that's important too. Okay.
So survival will not be an issue for you?
What?
Survival will not be an issue for you?
The which?
Survival.
Survival. Well, you have to make appropriate preparations to survive, but I would say that people who are going to go to Mars are going to be probably a lot safer, not just than any number of people who have volunteered for military service, but people who climb Mount Everest and do all sorts of things like that for recreational purposes. 10% of the people who try to climb Mount Everest die. But they don't want to do it. They spend a great deal of effort to prepare for it, to raise the money for it, to do everything. Yeah.
Yeah. What's the best stuff we should do right now if we want to be among the first people on Mars?
If you want to be among the first people on Mars, that's an interesting question. Okay, my standard answer is become an aerospace engineer.
I am.
Okay. Now, next, okay, now, until very recently, the next step would be to apply for the astronaut corps. But that, I mean, that's still a reasonable course. The other thing you could do is apply to work at SpaceX. Or if there's...
I did, in French.
Okay. Start your own SpaceX.
Yeah, I'm doing it.
And then you're doing the right thing.
It's true.
You know? Create your future. Yes, other questions? Sir?
Yeah, we've seen the development of heavy lift boosters technology like the new Glenn, for example, or VFR. But the habitat technology has been lagging behind. Do you think it will be ready in time? When?
Which technology is
the habitat?
The habitat?
Yeah.
Well, no, I don't think that's a problem. I think, I mean, I don't like the geometry of space station habitats. I prefer this geometry for a surface habitat, but that's a trivial change. You land space station modules on the surface of Mars or the Moon, you have a habitat. What they need, I mean, it's so stupid, a stupid space station. He wrote this letter to Bridenstine, trying to explain it. Okay. You have, okay, it's open to criticism, but okay, SLS, heavy lift booster. You've got Orion, that's a capsule that people can ride in and re-entry at Earth. What's missing for you to go to the Moon? A lunar lander and ascent vehicle. So they said, we can't go to the Moon because we don't have a lander. So we're building a space station in orbit around the Moon. The money they're spending on the space station in orbit around the Moon, they can use to build the lander. Then they could go to the Moon. Okay, so. Now, I actually think that we can even do the Moon with Falcon Heavies. Okay, we use a couple of Falcon Heavies, land a couple of halves on the Moon. They'd be smaller than what you can do with an SLS, but you could land a 10-ton habitat on the Moon. Okay, the same lander that lands a 10-ton habitat on the Moon could land something like the Apollo LEM, a lightweight vehicle on the Moon. Okay, the Apollo LEM upper stage weighed 2 tons dry, including the cabin. You're returning from the Moon and doing a propulsive capture in low Earth orbit. It's a delta V of 6 kilometers a second. You have a mass ratio of 4. You would need 6 tons of hydrogen oxygen to take a 2-ton vehicle. So it weighs 8 tons and also the same lander that is fully fueled on the surface of the Moon, and you come back to low Earth orbit, the crew could get picked up by a Dragon. And once you have propellant being made on the Moon, then when this comes back, you just refuel it in Earth orbit with 6 tons of propellant. You fly it to the Moon, and then it gets its propellant from the Moon, flies back to Earth orbit. And so this whole sequence can be done with the Falcon 9, supporting each mission to the Moon. But it's Moon direct. There you go. One chart. But no, I don't think the habitat is a tall pole at all. Other questions? Sir?
Yes, so Your Mars Direct architecture, how much do you think it would cost in the end? You said 10 billion, that's about the figure that NASA receives every year?
NASA receives 20 billion.
20 billion.
Yeah. It depends who's doing it. Okay. I believe that if NASA did it, and if they were in their purpose-driven mode, that is, trying to get things done in the shortest amount of time to the least cost, as they understand that, they could develop all the technology needed to do all this. Okay, the heavy lift booster, well, that's almost developed right now. You'll notice, by the way, this resembles SLS a lot. Okay, we designed this in 1989. The event. Okay, but here it is. It's probably to fly within 2 years. Okay, the habitat module and the Earth return vehicle, 1 stage gets you back from the moon, 2 stages from Mars. Developing that by an agency like NASA, if it's in its purpose-driven mode, $20 billion, and then each mission by the copy would be done for $2 billion to Mars, $1 billion to the moon. Now, on the other hand, if we're doing this, okay, for the moon, and this for Mars, this is Mars with 3 Falcon Heavy launches per mission. Okay. It's a variant of Mars Direct. We'll go into the details, but it's a smaller crew of 2 until you get the thing going. But you know, Falcon Heavy launches 120 million each, so that's 360 million. And then this stuff, you know, or this one, the recurring mission is a Falcon 9. $70 million launch vehicle. Okay, and of course the Falcon 9 has already been developed, and the Dragon has already been developed. So all you really need is this thing. Yes, I think if you told Elon Musk, create this for us, and we'll give you $5 billion, he'd be laughing all the way to the bank. Really. So it is, the question is the space program going to be purpose-driven or vendor-driven? Okay. I run a business. Imagine if I let my vendors determine my spending. They'd all be, give us money, give us money. You really need this, you really need that. Buy this from me, buy this from me. Okay. Now, a private company would go out of business in no time if it was run by its vendors. Okay. The government can be run by its vendors because it's got new tax money to burn every year. But that's what's happened to the manned spaceflight program. Interestingly, the space astronomy and the planetary exploration programs have insulated themselves from that because they've created these very elaborate structures of committees of scientists declaring priorities and so forth, and coming to consensus around particular missions. And then at that point, saying, we're going to land a rover on Mars. And so if someone comes along and says, but don't we need a Mars gateway first? They say, we're not interested in a Mars gateway. We just want to land a rover on Mars. Okay. And so forth. But anyhow, a purpose-driven NASA could do it for tens of billions of dollars. A purpose-driven entrepreneurial company could do it for well under $10 billion. Other questions? In the back.
You just mentioned that you have your own business, if I'm not mistaken, Pioneer Aerospace, and the new one in the energy sector. You've been highly involved with the political, educational, and also engineering part, but you are also involved in the entrepreneurial way. Why did you choose to build this company, and what are you aiming to that you can't do in the other kind of organization you've been involved with?
Okay. Okay, well, the energy company is now spun off. I'm not in the management of that anymore. But but yes, I still am the pioneer astronautics. That's how I buy groceries. And I mean, you know, I'm not just a public speaker. I am an engineer, and I have a lot of what I think are creative ideas, and I like to have a chance to develop them. And we have won over 60 NASA contracts because we have shown NASA that we can do this faster and cheaper than most of our competitors and do it well. And I relish that role as being a person developing new technologies that can help the development of space. While we have we've done small rocket engines and high altitude balloon systems and breathing systems and life support systems, my favorite area, and the one where over half of my work has been, more than everything else combined, are systems for taking materials on Mars or the Moon and turning them into resources. And that's what they call in situ resource utilization. I would call it in situ transformation of useless materials into useful resources. Okay.
Maybe we have time for 2 questions.
2 questions. Any of the women here have questions? No? French women not talking? What? Okay. All right. Well, have your chance. All right, sir.
You say we have to, on the life on Mars bit of your talk, which was very interesting. You say we have to go to Mars in order to find out more about life.
Mm-hmm.
One could argue that we've already been there with the Viking missions and with the rovers. And so at what point would you accept that there is no life on Mars and that it's a dead planet? Because some people say we've been there and we've, to the best of my knowledge, we've found nothing.
Well, no, we haven't drilled down to the reservoir of liquid water on Mars, which is 1 kilometer underground. We've dug a couple of centimeters into the surface in a few places. And, I mean, you know, Viking was a static lander, couldn't move. It had a repertoire of 3 experiments it could do. The experiments actually did result in release of the gases that would have proven the existence of life on Mars, but alternative explanations were found, leaving the experiment ambiguous. Viking certainly did not prove there's no life on Mars. It simply failed to prove that there is life on Mars, because given 3 experiments, which actually produced positive results, they were able to find an alternative explanation. And actually, I think their conclusion's highly contestable. Viking found no organics on Mars, and that was the evidence that was used to debunk or doubt the positive signals from the gas release experiments. But since then, we have found organics on Mars. So the Viking result that there are no organics on Mars has now been demonstrably shown to be false. And we have found water, well now liquid water, which is a habitable environment. We have found methane releases on Mars. And that's also very interesting because either that's biogenic or hydrothermal, which means it either is proof of life or proof of the existence of places that are friendly to life. And so, but in any case, the idea is, yeah, if we go to Mars with human explorers who can travel in a day more than all the rovers we've sent to Mars put together have traveled in the years that they've been there, and they find no fossils on the surface, no microbes on or near the surface, and nothing in the subsurface liquid reservoirs, then at that point I would say the evidence was weighing against life on Mars. But actually, I think that, I mean, I'd be willing to bet $1,000 that there at least was life on Mars at one time. Because Mars had liquid water on its surface when there was clearly life on Earth, and Earth would have been bombarding Mars with projectiles containing microorganisms. So Mars would have had life on it if from no other source than the Earth. The issue is, really, if you want to know, whether life on Earth came from Mars, or both proceeded from a common source, or both had independent origins. I think, look, here's a fact that we know. Life appeared on Earth virtually as soon as it could. That's a fact. Now, what do you extract from that? Either, one, the development of life through chemistry is a highly probable event that occurs as soon as it can occur, in which case there was life on Mars. Or two, there was life floating around in space near the Earth that was constantly landing on Earth and took root as soon as the Earth could support it, in which case there was life on Mars. Okay. Right? So the issue then becomes what sort of life? Life on Earth is a mystery in a number of senses. For one thing, we find no examples of free living organisms on Earth simpler than bacteria. Now, bacteria may seem to you to be pretty simple, and they are compared to you and dogs and cats and pine trees, but they're not simple, okay? Every bacteria has a complete DNA, RNA textbook written in it in the same alphabet that you use. Think about that. Okay, your book is as big as the Encyclopedia Britannica, theirs is as big as Les Mis, okay? But it's there, okay? Now, think about this. If you found, could a novel like Les Mis have been the first thing ever written by anyone? No. It uses the complete French language, which itself had to develop in many ways. It uses all the letters of the alphabet. It uses punctuation and so forth. And furthermore, it was printed on paper, which took centuries of technological development to create. Okay, there's a whole history behind that. Okay, let alone behind, say, this. Could not have been the first machine. Okay. So bacteria has the whole alphabet in it. Shouldn't there have been a simpler alphabet before there was the complete alphabet? Okay, so there are ancestors of bacteria that we don't see on Earth. Now, you could argue, well, maybe they were all wiped out by the bacteria. Okay, you could argue that, but that is just making an excuse for lack of evidence. Okay, and certainly the pattern in nature is that as more complex organisms have evolved, simpler forms have persisted. So we don't find the ancestors or anything like the ancestors of bacteria on Earth. So this suggests that bacteria may be an immigrant phenomenon, that they came here fully formed. It's just like, I was walking around the Latin Quarter where my hotel is here in Paris the other day, and I saw a Gothic cathedral. There are no genuine Gothic cathedrals in the United States, okay? Because those are medieval structures, and there was never medieval civilization in the United States. There are no structures in the United States that predate the late Renaissance, so we can know that Western civilization in North America is an immigrant phenomenon. It didn't develop here. And there. Okay, so bacteria appear to be an immigrant phenomenon. Now, Well, if we found nothing on Mars but bacteria of the same general type as what we see here, use RNA and DNA, and there's no simpler thing, that to me would suggest that we're seeded from interstellar sources. If we found similar RNA, DNA organisms, but also simpler types on Mars, then that would say life evolved on Mars and was transferred to Earth. Okay? If we find other organisms using a different kind of genetic code altogether from DNA and RNA, that would say that here's two planets, they were not seeded from a common interstellar source, they must have evolved indigenously, and I guess it must be the case that the more primitive varieties would work out. Okay? If we find no life on Mars, you won $1,000.
Last question, maybe.
Last question.
Very short answer, please.
All right. Fine. Last question. Yes.
It's more a question about food. One of the problems about doing a mission to Mars is, well, one of them we talk a lot about food, and because you need a lot of it.
Okay.
So how about water? That doesn't seem to be a problem on your spacecraft, but what would you put on that
food
and how much?
Okay.
Because it's going to be a
okay.
2.5-year mission.
Right. All right. Initial Mars missions will bring their food. Later on, once we have settlements, we grow food on Mars. Okay. But for a single round-trip mission, it actually is much simpler just to bring the food than to try to grow it. Okay. And then the food will be composed, in my view, of similar types of ingredients that you might find in a kitchen and refrigerator and shelf in Earth. That is, I would not send the crew to Mars with 1,000 meals ready to eat, like the Marines use. Okay, it's boring. Yeah, it's a problem. What we found, I mean, early in our program of the Arctic station, we did use stuff like that, and we ultimately rejected it, and now we just go to the store and bring up all sorts of foods. Given the limitations, we typically take mostly shelf-storable foods and only a small amount of refrigerated foods. But even so, the crew can take these different ingredients and combine them in a multitude of ways to create interesting meals, which you simply can't do with meals ready to eat. Now, I initially thought that cooking would be a chore, and in my cruise anyway, I rotated, each night a different person would cook dinner. We'd take dinner together, a different person would cook. In my cruise, which was an international cruise, we rapidly developed into a competition because different people tried to cook meals that in some way reflected the national cuisine and who could cook the most interesting meal. And this is why you should not include a British person on it. Okay. So that's an issue. But that's what I would do. And you can do that, especially if you have an artificial gravity spacecraft, which allows you to cook in conventional ways. The astronauts, they drink food out of squeezing tubes and things because they're in zero gravity and they don't want the food running around. You can't fry an egg on the space station, right? But you could in an artificial gravity spacecraft.
And how would it be scored? And so I suppose the 2 years would be transported with the automated spacecraft.
Yes.
How would be the 6 months?
Well, you store it. That is, you can look at water. You have to recycle because you use a lot of water. But if you think of how much water it takes to food. Okay, a person uses about 1 kilogram of food a day. If you got 4 people, it's 4 kilograms a day times 800 days is 3,200 kilograms, and if you pack that correctly, that's about 4 cubic meters of space to store that much food, and you have that available. So you do want to package foods in a way that they can be stored efficiently. They don't use a lot of extra space. I mean, if you look at your cupboard at home, you have these cans and stuff, and most of the volume is not effectively taken up. But, yeah. Anyway, and also one thing, I bring a bread maker. It's a good one, yeah, no, I mean, you know, bread, why is bread so favored in civilization is that it could be stored without refrigeration for long periods of time and then cooked into very tasty meals and be fresh, and you could store the flour for 2 years and you could get fresh bread.
Robert, now